So as I recall, this one did not have any max or min points. It generated an x value that worked, but when I subbed it back into the function, it failed. So I'm going to hunt now to see if this has any points of inflection to it. I'm going to need its first derivative. So df by dx is, got some product rule happening here. This will be 1 over 2 root x. That is e to the x. This is root x. This is e to the x. So factoring out my e to the x's, that's this taken care of and this taken care of, I'm left with 1 over 2 root x plus root x. And as in the last video, I'm going to acquire a common denominator here, which means I need a 2 root x in the bottom, which puts a factor of 2 and an extra root x in top, giving me df by dx is e to the x 1 plus 2x and 2 root x to the negative 1. Okay, so in order to do points of inflection, I'm going to need the second derivative of this monster. So you'll notice that it has 3 pieces, 2, 3, which means I'm going to have a 3-way product rule. And within that product rule, I'm going to have to do a chain rule for this one, right? It's a root x inside of a rational expression. So it's going to be a bit of a beast, but that's okay. We can do this. So d2f by dx squared is going to be derivative of the first, leave the next 2 alone, plus first, third, plus leave this alone, derivative of this one. And my big fat head is going to get in the way, but that's alright. Derivative of an e to the x is an e to the x. Leave this alone, leave this alone. Leave this alone. Derivative of 1 plus 2x, that goes away, and the derivative of 2x is just 2. Leave this alone. E to the x, leave it alone. 1 plus 2x, leave it alone. Now this one, the thing that goes in there, you drop the negative 1 in front, keep what's inside, drop it by 1. Now I need to do the derivative of the inside, which should be a 2. Bring the 1/2 down, keep the x, reduce its exponent by 1. 2 times 1/2, well, that's just gone. So I'm going to write this out. I'm going to try and clean some stuff up. First off, I have an e to the x in all 3 of these terms, so I'm going to just factor it out. In this front term, that leaves me with a 1 plus 2x over top of a 2 root x. It's this piece and this piece. In this piece, my e to the x is gone. That leaves me with a 2 over top of a 2 root x. And in this piece, once that is gone, I'm left with a 1 plus 2x. It's negative, so that's going to change. And I have a 2 root x squared in the denominator. And I have another root x down there as well. Okay, so I'm going to clean this up a little bit. 2 squared is 4. Root x squared is just an x. So if I were to scan across this and get myself a common denominator, the factor that's missing from this term and this term is a 2x. So I'm going to introduce that, top and bottom. So that will give me second derivative of f by x is this e to the x out front, and then this monster fraction, 2x times 1 plus 2x would be 2x plus 4x squared. 2x times 2 is another 4x, negative 1, negative 2x. All over top of this common denominator that I have established of 4x root x. Okay, so that can be cleaned up a little more. Second derivative of f is e to the x. That's my first piece. The next piece is this denominator. It's a 1 over 4x root x. And my third piece is this polynomial here. I have a 4x squared. I have a 2x and a 4x, which is a 6x. Oh, I have a 2x, a 4x, and a negative 2x, which is 4x's. And I have a subtract 1, like that. So now that I've got my second derivative done and then factored up, I have to finish this points of inflection hunt by setting this thing equal to 0. So I'm going to erase all this stuff except the main function in this line in order to try and do that. So case 1, e to the x equals 0, or 1 over 4x root x equals 0, or 4x squared plus 4x minus 1 equals 0. So I think you're hopefully getting the routine here for how this works. This thing is never equal to 0. So you don't even have to do any work. You can just scratch that one out. If you have only things in the denominator, that can never equal 0 either. So don't even worry about it. Never! Exclamation point. Now this thing is interesting. That's a quadratic. Quadratics either have 0 or 1 or 2 solutions. So this function might inflect nowhere, it might inflect in just one place, or it might inflect twice. The way you solve a quadratic function set to 0 is using the quadratic formula or by factoring. So if you're good at decomposition, then you could try your factoring skills on this one. If you are not good at decomposition, or you don't have faith that this has a tidy, clean answer, you just launch straight into the quadratic formula. So that would be x. Ugh, this marker has gotten goop all over me. X is minus the b value plus or minus the square root of the b value squared minus 4 times the a value times the c value, all divided by twice the a value. All right, so x would be negative 4 plus or minus the square root of 16 minus 4 times 4 is 16 times negative 1 would be positive 16 over 2 times 4 is 8. So x is negative 4 plus or minus the square root of 32 over 8. Well, that's bothersome. Oh well, it's just calculator work. So x is either negative 4 plus the square root of 32 divided by 8, or x is negative 4 subtract the square root of 32 over 8. So I'm going to get my calculator out and I'm going to work out those two values. Alright, so square root of 32 is around 5.66. Check 4 divided by 8 is 0.207. Now we could render that in a reduction of radicals, but for what we're doing, I think just decimals will do. On this side, we have -4, subtract the square root of 32 divided by 8, which gives us -1.207. Alright, so it's symmetrical around, well, it says symmetrical around a half maybe. Okay, so as with the max mins, I have the horizontal location of them, but I need the vertical. In order to get that, I'm going to have to take each x value, dump it in the function. So I'm going to give that a try once I erase some of this mess. So the function at 0.207 would be the square root of 0.207 multiplied by e to the 0.207. Pop that in the calculator. E to the exponent 0.207 is around 1.23 multiplied by the square root of 0.207 gives me 0.5596, so I'm going to round that up to 0.56. Alright, I had a number that I got from my second derivative equaling 0. I found its y value and it worked. Therefore, there is a point of inflection at 0.207 on the x and 0.56 on the y. Okay, the other option is to pop this into the function. F at -1.207 equals the square root, should be in yellow, times e to the -1.207, and immediately this is problematic. You can't take square root of a negative, so this one is going to fail. So what we figured out is that this function, f of x, has one point of inflection at 0.207 on the x and 0.56 on the y. So whatever it does on either side of that point, when it comes to 0.27 on the x, it either has to be curving down and then flip to curving up. It's got to do this sort of thing. Or it has to be curving down and then flip to curving up. I'm going to clear this off, try one more, and then I think we're good for the problem sets. To get the points of inflection for this function, like the other one, I'm going to have to get the second derivative. So to get second derivative, I need to do first derivative. This one we already went through. It's a function in a function, so there'll be some chain rule architecture here. 2 layers deep. Derivative of a ln is 1 over x, whatever is inside of it. And the derivative of 2x plus 1 would be just 2x. So I end up with this derivative being x squared plus 1 to the -1 multiplied by 2x. When I go to do the second derivative, because I now have a thing times a thing, it will be product rule. And because this half is a function in a function, I'm going to need chain in order to do that portion. So if I build out my infrastructure here, d2g by dx squared will be a product rule piece that's big enough to fit in a chain rule. Leave that alone, plus leave this alone, and then derivative of the last piece. My chain rule stuff is going to go into here. Alright, so the derivative of anything to the negative 1, you bring the negative 1 in front. X squared plus 1, raise it to negative 2. Derivative of the inside will be 2x. Leave this one alone. Then I have x squared plus 1 to the negative 1. Derivative of 2x is 2. So cleaning this up a little bit, d2, that's not the color I want, d2g by dx squared. Alright, I have a negative here, and then, let me do this different color, it's easier to see. I have this negative. This piece is in the denominator, and then this is in the numerator, as is this. So 2x times 2x would be 4x squared. And I have an x squared plus 1 in the denominator, squared. From this term, I have a plus 2 in the numerator, and an x squared plus 1 in the denominator. Those are fractions, so to do the addition or subtraction with them, I need a common denominator. So I'm going to have to introduce another factor of x squared plus 1 in the top and the bottom here. So cleaning that up, I'd end up with d squared g by dx squared is a negative 4x squared. 2 times x squared is 2x squared, and 2 times 1 is 2, all over x squared plus 1 squared. And I have some x squareds that I can gather there, so that the second derivative of g simplifies to 2 minus 2x squareds over x squared plus 1 squared. So like all points of inflection, I'm going to have to separate this as two pieces and then set them to 0 and see what I get, but I will need some space to do that. So this thing has a numerator and a denominator, so I'm going to be able to split it as this polynomial part and then a rational part. So case 1, case 2. So under case 1, the 1 over x squared plus 1 squared equals 0, and in case 2, the 2 minus 2x squared equals 0. Well, we've gotten into a theme here. You can't get 0 through division, so this is never going to work. Here, I'm going to kick my 2x squared to the other side, divide both sides by 2, square root. And because I called the radical as the antifunction for the square, I need to keep the plus or minus. So x is plus or minus 1. All right. So I have the x locations. I just need to get the y's. And the y's, I get them by putting the x value into the original function. So g at 1 will be the ln of 1 squared plus 1. So g at 1, the ln of 1 squared is 1 plus 1 would be 2. So this is approximately, whatever the ln of 2 is, it's going to be a little bit less than 1 ln of 2 equals 0.693. So I was able to put that x value into the function and get a viable answer, so no problem. G at negative 1, if I put that in there, ln of negative 1 squared plus 1 will be, so negative 1 squared is 1, 1 plus 1 is 2, which is going to give me exactly the same answer. So what we've just shown is that g of x has 2 points of inflection, POI, one at positive 1 on the x, 0.693 on the y, and another at negative 1 on the x, 0.693 on the y.